Welcome to Mathematical Colors and Codes, Episode 6. I'm Sandy Eklund, and I'm a librarian here at City of Fairfax Regional Library. So far in this series, we've looked at prime factorization and non-decimal bases, and we've used them to make coded messages in many different ways. Today, we're going to look at one more non-decimal base, base 2, which is also known as binary. Now, base 2 would be like being on an alien planet where, sure, you have two arms, but you don't have any fingers. And so they might count something like this: 1, 10, 11, 100, 101, 110, 111, 1000, 1001, 1010, 1011, 1100, 1101, 1110, 1111, 10,000. And that's really confusing unless you see it written out. So let's go to the computer and look more closely at binary. All right, so here's binary written out going from 1 to 26. And the idea is the same as the other non-decimal bases. If you remember, well, in base 10, we've got the digits 0 to 9. In base 6, we've got 0 to 5. In base 5, we've got 0 to 4. So in base 2, we're going to have just 0 to 1. But that means you only need two symbols to represent it. So you could use two colors, two shapes, two sounds. Computers use binary because all they need to do is use on and off. So it's easier to physically represent. Now, the big catch to binary is it takes a lot of space to write it out, so it's not as practical for humans. But let me go over how it counts. So A is 1. But then it's like we got to 9 in base 10. That's 1 is as high as the digits go. So you need to go over another place. It's not a decimal place, it's a binary place. And B is going to be 1, 0. So in base 10, we've got the tens place, the hundreds place, the thousands place, and so on. In base 2, we've got the twos place, the fours place, the eights place, and the 16s place, and so on. So B is 1, 0. It's got a 1 in the 2's place and 0 in the 1's place. Then C is 1, 1. Then you've run out of room, so you need to go over another place. So D is 1, 0, 0. Then 1, 0, 1, 1, 1, 0, 1, 1, 1. Now you need to another place. So 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0. 1101, 1110, 1111, and now you need another place. So it's 10000, and so on. I'll let you read it from there. It goes up to Z is 11010, and you can check that. Z has a 1 in the 16's place, a 1 in the 8's place, and a 1 in the 2's place. And sure enough, 16 plus 8 plus 2 is 26. And you know Z is the 26th letter. So that's how it works. Let's look at some messages with binary. Or first, let's try it with your name. For my own name, I'm just going, I look up all those codes, and S is 10011, O is 1111, N is 1110, D is 100, R is 10010, and A is just plain 1. So if I want to make a coded message for this, I just need something for 0 and something for 1. So now let's look at a message in binary. First, I did it with numbers, but I can also put that into shapes. And I picked, in this case, I picked diamonds and squares. So a diamond is 1, a square is 0. And that's what it looks like with shapes. But then to figure it out, I go back to the chart And it turns out the first word is beautiful and the second word is binary. So that was a long way to say a short message, but there it is. Okay, you could also do it with colors. And which color has to be one? If you look at the way I did the codes, every letter starts with 1. So red is 1 in this case, and blue is 0, and we can figure that out right away. And then we go back to the chart to figure out what each letter is, and this turns out to say nice numbers. So that's binary. Again, it's not super practical for messages, but you can, but the one thing about it is a lot easier to do because you only need 2 things. Somebody wrote to me on my blog that they use this in knitting. They use binary because they can just do the 2 basic knitting stitches to write a message. It's also good for birthday cakes. This is a picture of my son's birthday cake when he was 19. So rather than put 19 candles, we just did 19 in binary because it's 16 plus 2 plus 1. So I have lighted candle, off, lighted. So it's 10011. The fun thing about this is the same time my youngest was 19, my older kid was 25. So it turns out that I could have turned the cake upside down because 25 in binary is 11001. So it's a very handy way to represent age, though you probably, it's more useful when people get really old. You can keep their birthday cake from being a fire hazard this way. And binary codes are used by computers. I looked on the internet and got this ASCII table, and you can see it is a code in binary for the letters of the alphabet. And they've got different codes for capital letters and small letters because this is what a computer uses to know what it's going to print out. And binary codes are very hard for humans to read, but they're very handy for computers because they can store them with just an on-off switch. Okay, we have looked at prime factorization. We've looked at base 10, base 6, base 5, base 2. Now you can take these ideas and decide where you want to go with that. You can make your own code with any of these methods. Maybe you'll come up with another method, use a different base. You can use colors, you can use shapes, you can use stitches, you can use candles, you can use Legos to make any message you like. And I hope that you've enjoyed thinking about these ideas.
Okay, because I'm a librarian, I want to finish up this series by talking about some books that can take you beyond the ideas I've presented. And the first one has a special place in my heart. It's called You Can Count on Monsters by Richard Evans Schwartz. This book does kind of the same thing I did with my sweater. It shows prime factorization, but instead of just using colors to represent the prime numbers, this author uses monsters. So here's a 2 monster representing the number 16. 2 times 2 times 2 times 2. And he makes a new monster for 17, and so on. You've got prime monsters, and then for composite numbers, there's monsters combined. Another book by Richard Evans Schwartz that goes even farther is Really Big Numbers, and this one blows your mind about how big numbers can be. Once you think you've gotten to the biggest possible numbers, he takes it a step further. Another book is called Which One Doesn't Belong by Christopher Danielson, and this one is also mind-bending. You've got, on each page, you've got 4 shapes, and it asks the question which one doesn't belong. Well, it turns out that every shape is the right answer, but the challenge comes in figuring out why. Okay, if you liked the coded messages part of this series, 2 books you might want to check out are The Code Book by Simon Singh and Top Secret by Paul B. Ginesco. Now, the final 3 books I'm going to show you are not library books, I'm sorry to say. However, I think you'll understand why, because they're coloring books. So we couldn't let you color in library books. But the first one is called Patterns of the Universe by Alex Bellos and Edmund Harris. And it's a coloring book with math ideas. Here's a multi-Venn diagram that I colored. But the whole thing presents some math ideas and then patterns you can color using those ideas. And a follow-up to the book is Visions of the Universe, also by Alex Bellos and Edmund Harris. And another coloring book with the same idea is called The Golden Ratio Coloring Book and Other Mathematical Patterns Inspired by Nature and Art by Steve Richards. Again, I'm sorry they're not library books, but I found these on Amazon. Thank you for watching Mathematical Colors and Codes, Episode 6, our final episode. Now, if there were any episodes you missed, you can search on YouTube for Mathematical Colors and Codes, and be sure to look in the description for the link for the coloring pages you can download with each episode. I hope that you enjoyed these as much as I enjoyed making them, and I hope that they helped you to have some fun with math.